Hi there, this is Mr. Sandin, and I'm going to describe to you what you should be thinking about for free body diagrams. Now, free body diagrams, all they are is just a diagram showing the forces acting at the center of mass of an object. So we don't know exactly where the center of mass of this object is, but let's just assume that it's in the center of the object itself. Sometimes the center of mass can be a little bit off to one side or the other, but we'll just make it simple, put it right in the middle here. So what forces are acting on this object? Well, first we have to describe this object. What's it doing? Let's say that this object is just resting. It's just, this is a box and it's resting on, let's say, like the ground, a very flat surface. So what forces are acting on this? Well, we've got, in my mind, we've got two forces clearly acting on this. One of them always is gravity, and gravity always especially on Earth, is going straight down in any one of these problems. It's the force due to gravity. So that's always pushing, or pulling, I should say. Pulling is a field force. It's pulling down on every object that we consider that's on Earth. And if we just say that there's an object anywhere, like it's on a table, it's on a surface, just assume that it's on Earth unless someone tells you it's not on Earth, in which case then we can start drawing different kind of force diagrams. But on Earth, there's always this FG going straight down. Now, if this was on an angle, let's say like this surface right here was on an angle. This is important. Let's say that the surface is like this. I'll draw a little one right here, like this, and the box is kind of like this. There's a center of mass for the box. Oftentimes we talk about skiers in this kind of situation where we have like a skier on a hill. The force due to gravity is not going perpendicular to the hill, it's going straight down again towards the middle of the earth. It's always going straight down. Okay? So here the force due to gravity is going straight down. Now, if this box up here, if this box is just sitting there, there's no motion at all in this, it's just resting, then if this force is right here and there's no force opposing it, then that means this box is going to be moving this way. It's accelerating in this direction right here. So how do we show that this box has forces acting on it and yet it's not moving? The way you do it is you show the contact force, which is the normal force, the force at the table on this box, is going in the exact opposite direction. This is the normal force. I sometimes write with a lowercase n or an uppercase n. It doesn't really matter for this. So in this case right here, if you add this force vector, okay, so it's got a direction, it's got a magnitude, it's a vector, to that vector right there, so I'll just draw it out like this, oops, this force vector, and we do the tip to tail method, so that's the normal force, and we add that to the gravitational force. So tip to tail, it's going to go right back down, oops, right back down to there. That's a gravitational force. And the resultant is going to be nothing. It doesn't go anywhere. So if you add these two vectors together, tip to tail, so you put, let's take this whole vector and we can put it at the tip of this one. It's going to go right back down to the middle. It's going to go back to where we started from. So that means that the overall sum of all of these forces, we write the sum of all these forces added together. So that's Fg plus, I'll get the right color here, Fn, the whole thing will equal 0. Okay? That means that this object has no net forces. No net forces. There's no force winning in this situation. They're canceling each other out. No net forces. Okay? Now, if this object was moving beforehand, okay, if it was moving, and there's no friction here, so let's say, okay, so this, before it was not moving, it was motionless, it was just staying put. But if this thing was moving, let's just say it had a constant velocity of, let's just say like 2 meters per second, and it was moving along, chugging along this direction to the right. This is still the accurate force diagram for that object if it was moving at a constant velocity at 2 meters per second. Okay? Why would that be? We can't show that this is moving with our force diagram. especially if it's a constant velocity. It could be moving at a constant velocity. This is just one instance of a constant velocity, which happens to be 0. 0 meters per second if it's just sitting here motionless. But if this is 2 meters per second, it's moving, it's chugging along here, there's no force pushing it in that direction. There's also no force resisting it. You could say, if you wanted to make this a little bit more complicated, you could say this box is being pulled. We've got some sort of a rope attached to it right here, and there's also, this is a bumpy surface or just any kind of surface. So there's going to be some friction there. So we could say that, all right, well, yeah, this box has got a force. It's pulling it this direction. So that's a force due to the tension on this rope right here. But then we've also got a force going backwards due to friction. Now, if this force due to friction is the same length as this force right here, it's got the same magnitude in the exact opposite direction because it's going against its motion. If it's exactly the same, that'd be the force due to friction here, then this could be a constant velocity going in this direction, going to the right here. Okay? It would not be speeding up, it would not be slowing down, but the force would be exactly canceled by the frictional force. Let's say instead, just for argument's sake here, that this force is a little bit smaller. I can ask you this question. I can say, okay, if this is a little bit smaller than this force right here, what is the overall, is this object accelerating? Is it going at a constant velocity? Is it a 0 velocity? What is it? You could say, well, if I add all these forces up, so this normal force would obviously cancel with this gravitational force, just like we saw up over here. But these two forces, let's see what happens if we add them. If I give you an actual kind of like, if I give you like an angle right here and an angle right here, then you could answer this pretty easily. But let's just say, we're not going to get into that much detail right here. Let's just say that this is going exactly in the opposite direction as this. They're just at 90-degree angles from this normal force and this gravitational force. So if you add this tension, the force due to tension on this rope right here, and you add that to the frictional force, going backwards like this, you're going to get an overall force in the right direction. So the overall force, again, I didn't give any values to this. I could have given some values. I'll just do that right now. So let's say that this force is 5 newtons, and that this force right here, this orange frictional force, I didn't label frictional force, let's say that it is, let's say that it's 2 newtons. And we can even give it a direction, let's say it's -2 newtons. Because it's going in that direction over there. We're going to assign that as the left is negative. So if you add these two together, the sum of all the forces here, the sum of all the forces in this, that's the sum of, that's what that little Riemann sums means. Sum of all the forces, 5 plus -2. Overall, we're going to have a 3 Newton force in the right direction. So that's our overall force is going to be in this direction. So that means that our force is 3 newtons to the right. So we can, if we know what the mass of this object is, we could even say, all right, well, if that's the force and we know the mass of this, we could figure out what the acceleration is because F equals ma. So we could say, all right, so ma equals 3, so 3 newtons. So then if we divide this by the mass, we could figure out what the acceleration would be. Okay, whatever that mass is. All right, so I hope that makes sense that the forces, if you have forces that are completely canceling each other out, like this normal force and this gravitational force, then that means that there is no acceleration in this vertical direction. If you have an object that has a force that's kind of outweighing the other force over here, then it's going to be accelerating in this direction. If these forces right here would cancel out, that means that this object has a constant velocity. And one instance of a constant velocity is 0 meters per second. It means it's not moving. But it could be that it has a constant velocity that is 2 meters per second or 3 meters per second. whatever it happens to be. It just means that the forces are canceling each other out. You're not accelerating at all. You're just moving with the same velocity because forces make you accelerate. So if they're all canceling each other out and you get an overall sum of all the forces is 0, all we can say in that situation is that you have a constant velocity. So if you have a constant velocity, one instance is 0 meters per second. That means you're not moving. But you could also have a constant velocity of, let's say, 2 meters per second, or negative 2 meters per second, or 57 meters per second. You don't know what the constant velocity is. And in these free body diagrams, it doesn't give you that information because it's just working on what your intuition is for these free body diagrams. So let's go over a problem that might seem like it should have like a thrust or some kind of force, but it doesn't actually. Let's get a new one of these. Okay. Let's look at, let's see here. Let's look at a tricky one. I'm going to look at, hold on a second, sorry. Okay, this is a good one. Yeah, this is a good one. So let's say we got a box. Here's a box. Here's a orange box. It's got a box. Here it is, and here's a flat surface. But it's got friction. So we do have friction here. Let's say it's got friction. All right, and the object is slowing due to friction. Okay, so the object was moving, or is moving. Let's say it is moving. That's in this problem. The problem is the box is moving, so it's moving, but it's slowing. But slowing because of friction. All right, so we know a couple things. We know that this box is on Earth because we haven't said it's anywhere else. So from the center of this box right here, we're going to say, okay, it's got FG. It's not accelerating off of the surface. It's not jumping off of the surface, or it's not going down below the surface. So that means that this gravitational force is countered exactly in the opposite direction by the normal force. So it's important that you draw these vectors exactly as close as you can to the same length. So this is absolutely canceling out that. So the sum of these two forces is going to be 0. It is not going anywhere up or down in this vertical direction here. Okay? But in this now, we're saying, okay, it's moving, but it's slowing. So it's moving, but it's slowing. So when I say slowing, you should start thinking now, okay, I remember hearing about slowing in the previous unit when we're talking about acceleration. This is an instant of negative acceleration, or it's also negative acceleration or deceleration. I think that's how you spell deceleration. Acceleration. Okay, that's probably not right. Okay, right. So when this happens, when you have negative acceleration, you should be thinking, okay, yeah, that means that there's a force acting against this motion. So there's a force going against this motion. If this thing was moving to the right, and there's a force moving